This video is supported by the National Science Foundation. Hello again, everyone. I hope you had a great time going through the previous lectures with my team, learning more about reverse engineering and the utility of image analysis and machine learning techniques in its workflow. Now let's recap. During the series, you learned that reverse engineering is essential for hardware assurance, obsolescence, and intellectual property protection. But what was hidden from you are the complexities limiting the practical use of reverse engineering. Now let's dig into that a bit. Reverse engineering is an ad hoc process. That means that there are non-standardized steps in the workflow. Think of it as a recipe. Changing the ratio of one spice will alter the taste of the dish, right? Reverse engineering is just like that. For instance, take depackaging for example. Depackaging can be performed using mechanical or chemical means, each with its own benefits and limitations, like various flavors. Next, each IC can be designed and manufactured by a variety of parties at various node technologies. So each IC can have varying amounts of layers and features. So there's a high likelihood that reverse engineering of a new and unseen IC can be a very unique experience. Basically means that the features that you're learning cannot be generalized to all cases. Now, with billions of transistors and complex functionality, a large amount of information needs to be extracted and processed for hardware assurance. We have seen reverse engineering timeframes for a simple IC go from a few days to a few months. And it's highly likely that an anomaly might slip into the workflow. For example, the region highlighted as error in the image is from carbon deposition on the surface of the chip. The underlying feature is not clear, and this situation creates an ambiguity in the reverse engineering process. One of the possible fixes results in the correct design, and the other one results in an anomaly. But has this IC truly been tampered with? Yeah, it's a cliffhanger. Now, acquiring the functionality of the recovered design requires some subject matter expertise. For instance, as an experienced researcher in applied AI myself, I may be able to resolve and recover the design, but I won't be able to understand the functionality without access to specialized knowledge informing me about the nature of each cell in the design. And yep, that's most of the limitations of reverse engineering. We can condense the entire list into two main observations: scalability and repeatability. Scale by acquiring and processing large amounts of data accurately and efficiently without human intervention, and repeatability by ensuring lower dependence on non-standardized ad hoc steps and prevention of anomalies from entering the workflow. Easier said than done, right? So how do we address these limitations? We go with a tried and tested method of injecting AI into the workflow, but not the usual method in which we choose a model and let the model figure out what to do from the data, the purely data-driven methodology. We are better, so we break down the problem into explainable chunks. One of them you probably figured out from the previous lectures, the denoising and segmentation of SEM images. There are way more interesting ways of integrating AI into the workflow. For instance, we can automate the acquisition of SEM images from the sample IC. The processing can be automated using techniques like flip-side milling using a focused ion beam, and image acquisition can be automated by automating the SEM. Next, segmentation can be automated by using a variety of machine learning and deep learning methods. We found that deep learning-based segmentation models are the most effective. However, this required ground truth labels to be made available. We found this to be a way more challenging problem since labeling SEM images for each layer proved to be labor-intensive and time-consuming. Instead, we developed machine learning approaches that utilize the statistical properties of the SEM images to perform segmentation without ground truth labels. The first method, called histogram-based automated segmentation, relied on approximating pixel intensity distributions for material to perform segmentation. The second method leveraged noise in the SEM image to bound areas in the image with constant noise signature. In simpler terms, it used texture to segment the image automatically. The added knowledge on the statistics of the image helped automate the segmentation process without ground truth labels. As for the errors that slipped in, impeding methods and generative AIs can identify and correct corruptions and anomalies in the acquired images. Finally, the quality metrics for segmented images like those of structural similarity, SSIM, intersection over union, IOU, and mean squared error, MSE, can help assess the accuracy of the segmented images. But just like with segmentation, this part requires access to paired labeled image data as well. Instead, our works investigated the possibility to capture design rules of an IC. These rules implicitly capture information about the design that are very similar to the labeled ground truth image data. In our recent work called Secure, we developed a self-learning metric that captures design rules from noisy, weakly segmented images, bypassing the entire requirement for our ground truth label data. Combining these developments together, a novel AI-enabled image processing pipeline can be developed that can automatically acquire and extract information from the SM images in a robust and reliable fashion without human intervention whatsoever. Even operations that require expert assistance can be simplified. In functional validation, standard cells can be recognized by identifying patterns in the image that always occur together. Identifying these co-occurring patterns can reveal the standard cells used by the foundry automatically. This reduces the workload on the expert since they don't have to identify all the billion gates, but only a few ones that have been narrowed down by the algorithm. One of our preliminary works that's noted there does just that. Now, another limitation that prevents the adoption of reverse engineering are the intellectual property rights. Most of the designs that are used to train and develop models belong to IC designers, and proliferation of these designs is detrimental to them. AI even provides avenues to sidestep this problem. There are several privacy-preserving methods to share data and models of sensitive nature. Generative AIs can even make synthetic images, like they did with deepfakes, that look real, preserving all the statistics of the real images but are not part of the real design, hence obfuscating all the sensitive information. Integrating AI at the right place and for the right problem can produce overwhelmingly effective results, turning a very complex problem into a simple but plug-and-play scenario. This holds true not just for hardware assurance, but for almost every problem out there. I have highlighted some of our papers that discuss the open problems in this domain for those of you who would like to take a crack at it, and the data is also provided openly for you to experiment and learn with. I hope you enjoyed this course and found the content informative. If you have any questions on the course, please reach out to one of the instructors. Also, remember to follow us at FINS to keep up with our cutting edge research. And once again, thank you for attending and going through the course with us. See you again.